Hi, good morning, and welcome to the ZP Developer Zone. So we do this Developer Zone every Thursday at 8 a.m. London time, and I apologize because we're 22 minutes late today. The reason being is I'll explain it as I go through the slides. So today is approximately 8 a.m. London time, 24th of November 2022, and every week we like to just answer questions that have come in and sort of answer questions mostly of a technical nature during this webinar. So you don't need me to tell you that we have the ZP Academy free. There's free courses on there. We do webinars. Here's a webinar. We're actually doing a webinar at the moment live in India. We do collaborations. We have jobs, and we have the ZP Developer Zone where we like to discuss. We like to discuss all things technical in terms of biosensing. We also have workshops. Okay, so I'm talking rather fast because we do have workshops going on at the moment. So just for your interest, there's two workshops this week in India. I have colleagues in India, and I'm also participating as well. And so we were at IIT Bombay and also at SSN College in India. We do have a workshop next week in Norway around electrochemical biosensing and what's called IVD, in vitro diagnostics. We have one in Coventry, the UK, on the 22nd of December, and we also have one in Grenoble on I said the 22nd of December. We have one in Coventry, and we want to have one in Grenoble in December. And I do have a link here to those workshops. I'll try and make sure I put the links underneath the YouTube video afterwards. It's also probably worth saying that we do have because we are doing a lot of these live workshops at the moment. We've done ones in Norway now. We're doing ones in India. We've done one in California. We've got one in France and one in UK planned. People are saying, well, this is not close to me. So we are actually doing a workshop on the 10th of January 2023, which will be completely online, but I will make sure that we get the cameras into our lab, and we'll do live demos as well. The guys are really good at doing live demos and setting up multiple cameras so that you can get a good experience. Right, now I'm going to speak rather fast. We've got questions that came in about bespoke screen printed electrodes. We have these workshops running this week in India. I'm literally in the lunch break for India. So and then we also have some questions that have come in on SPEs from Canada. And I put the locations in just to help the people who've asked these questions locate where their answer will be, because then you can sort of fast forward. First of all, about bespoke electrodes. So I've taken the question here, and the questioner is kind of asking, they're a user of our hypervalue electrodes, so I'm always appreciative of people who use our stuff. It's really appreciated. I really like the hypervalue electrode. It's the electrode that we make in the highest volume. Every batch we make sure that we go in there and we do about 150. We take sheets from the batch. We check them by cyclophotometry. Make sure the RSD, the relative standard deviation, is really good. These things are really checked, and we put a lot of effort into these. So I'm glad that you're using it. The question is that they've really got is it ideal for their usage? And their usage I'll sort of discuss in a bit. I would say when thinking about low cost sensors, if you're looking for good design ideas, don't outthink it. Just go and look at a glucose strip. Here's a glucose strip. Glucose strips have been around for like 30 odd years now. This is one that I took a picture of. And what's interesting is the issue or risk of people putting their fingers on the sensing area is eliminated on a glucose strip, because in fact it's covered up by a microfluidic capillary. I've also got a video in a minute that shows how a glucose strip is actually used in operation, because the questioner has lots of questions. And what's really interesting about it is they've used the hypervalue electrode. They're not questioning its performance, its materials. They're actually questioning its usage. So the question is almost like, can you do this? Can you do that? It's actually the question back to them is, do you have a product design let's say, yeah, they basically need product design, and I'll discuss product design and user requirements in a little bit. So if you're trying to, as I say, just highlight a couple of features of a glucose strip, the sensing area is at the end, but people don't put their fingers on it because actually there's it's covered up by a microfluidic cartridge, let's say. And I think people tend to grab them in the middle, but I've actually got a video about using a glucose strip. So I will run this video in a minute. This is a video that I made. Why do I love electrochemistry? Because things can be intrinsically low cost. Now there we are. I've got my finger over the end there. You saw it, and I'm handling it quite a lot, but it doesn't matter because in fact as long as you construct the materials correctly, and this is something we do at ZP, then it doesn't matter. And I will prick my finger. I have to massage my finger to get enough blood. There we go. And then this is important. The way that wicks up. Now, when it wicks up, by the way, it automatically starts the assay. If you're using our hypervalue electrodes, that feature of where blood can wick up and automatically start the assay, that's intrinsic in the way we design the electrodes. So if you're ever wondering why our electrodes are rectangular and they have a certain layout, it's literally because of this feature alone. So I think we're the only people who make an R&D electrode that's available on the market with this feature that it's called an autofill trigger, where you could put a microfluidic on top of it, the blood can come in, or the urine or the saliva or wherever you're testing, and automatically start the assay. Otherwise, circular designs are designed with the idea of laboratory R&D and the idea that you're going to pipette on top of that electrode, but there's no consideration for actually making real products. So when you look at glucose strips, there's a distinct layout of electrodes, and our layout of electrodes is because some of us at ZP, including myself, have a long history of actual medical diagnostics and development, and it's I have some academic background. I'm a honorary professor at Swansea University, but we really have a long history of design and development and making of medical diagnostics. So the quick answer to this person is, if they want to avoid putting fingers on strips or on sensing, go for capillary fill. I think it will solve lots of problems. Their other question was really, well, if I just increase the size and stuff like that. So increasing the size, I don't want to say is a really bad idea, but I'll try and use our website to help answer the question, or try to sort of put people off. Not, people can make their own choices, but this is just a calculator, custom screen printed electrodes. I mean, this is just to give you a quick idea, right? So this is our standard size of electrode. And it tells us that if we sort of produce 20 sheets, then it sort of tells us what kind of costs we could expect to get to. So what I want to do is, let's say I make this up to a real volume of manufacture. So we're talking about really doing it at high volume. We're talking about like 3 cents, 3 US cents per sensor, let's say. Now, what I want to do is I want to, just increase things a little bit. 35 millimeters, 10 millimeters. Let's just make it a little bit larger. What will that do? Well, it just doubled the price. So be really careful about using size in order to overcome some use concerns that you have. We will do size, but size is not for free. It will impinge essentially cost. Now, what I'm going to do now is go back to my presentation and say, yeah, you can move things around, you can make things bigger, but size has a penalty, and size basically increases cost. They ask here whether they can print a line or something so that the end user knows how much volume to actually add. This is the same sort of video as previously. This is something that we do. It's called capillary fill, and you don't need to have lines and stuff like that. If you have a capillary fill designer, this is something that we can do for you at volume. It's no issue. The sample just goes in and automatically stops. It's really elegant, so it takes in the volume, and that's really important because it removes the user from being part of the variability. It just fills itself and it fills its own volume, so it controls volume and the filling. It's really important because otherwise you have a variability due to the sample addition. And also that design will allow you to have, again, the fill trigger that I was talking about earlier on, that the sample goes in, covers the first electrode, covers the second electrode, covers the last electrode, at which point then it would actually, if you design your electronics correctly or you're working with us, then the electronics would trigger and you could have a fill trigger and just start the assay automatically, which then reduces another variable. We can do something simpler as well, just have a sort of a spot like that, and that will kind of keep the sample in place. It could also help you guide people away from actually touching that. It sort of makes it quite clear that that's something not to touch, but maybe the capillary fill is more elegant. If you've got an elderly user population, sometimes these small electrodes can be essentially too small, at which point then we can actually do something like this, make it into a credit card type format. I would, so we're quite used to putting sensors actually on credit cards. That is an option. I mean, this is also an option as well. It's this is something that we've developed and we manufacture it. There's a sensor in there, but the sensor is essentially in a secondary housing. So even if we did the credit card, we would use the credit card as a secondary housing. Gives you something to hold, and it's quite nice to hold as a credit card. And this, again, that sensor is in there, but that's really a secondary kind of housing to hold the sensor. So there are many ways of making sensors more handleable, and you didn't have to intrinsically make the sensor itself bigger. You could actually just make the secondary housing bigger. I will, and it's also worth saying that we've actually got, these are designs that we have for handling things like the credit card format. And by the way, just for your interest, this can handle up to 6 analytes at a time. I'm going to go quickly, but if you've got any questions about this, please contact us at Zimmer & Peacock. So there's the credit card slotted in there. This is just in general, anyone who's developing a medical diagnostic and needs what they call an MVP, minimally viable product. We do have a really nice platform for this. If you Google Sense It All and Zimmer & Peacock, you will find this platform. It allows us to develop some sensors pretty quickly. It allows us to put them into our meter. You can see our meter being used here. This is an MVP. The reason I say MVP is because that's a black box and you might want something a bit more elegant. But I am going to talk about product design in a minute. In fact, the previous slide showed you some much more elegant designs. But this is an MVP, and what it allows you to do is it allows you to put sensors into the meter. The meter is really versatile, by the way. It can do all the voltammetry that you'd ever think of, square wave, differential pulse, cyclovoltammetry. It will do amperometry, pulsed amperometry, anodic stripping voltammetry. It will do potentiometry, no issues. Now what happens is the app, which is a really important part, the app will tell the meter what to do. So you'll tell us how your assay runs. The app was then programmed accordingly. The app tells the meter what to do. The meter gives the data back to the app. This is a really important part, especially in your development phase. The app will send all of the data to a cloud system that we have called Julie. So you can literally get the raw data out of the field test and into the cloud. That's really good because then you've got the custodianship over that data. Otherwise you have no clue sometimes where your data is, or your data's kind of saved on a memory stick or on a memory card and it's not in the cloud. Once it's in the cloud, you can share, you can have collaborations on it. And by the way, don't worry about patient data. You don't need to put patient names and ages into that. You could just have a patient ID. So it does allow you then to avoid the concerns around about putting patient data in. This is an MVP platform. It's designed to get a sensor fairly quickly, get a meter fairly quickly, get an app fairly quickly, get the data to the cloud, and you can start doing preclinical type trials or raising investment. And we can convert, no problems, the raw data into the units of interest. I think finally here, so they're asking here, they're really asking how is all, if they make the sensor bigger or they mess around with the hypervalue, how is this going to, affect the price? And so my answer to this is not a question of science or engineering. This is really a question of usability versus cost. This is really a question of product design, manufacturing, and user requirements. This is something that at Zimmer Peacock we're unusual because actually we can print electrodes, we can functionalize electrodes, we can design electronics. But the question really is about when you're asking questions about what about get my finger on the sensor? Can I make it bigger? Will the user be able to handle it? Should I go for credit card size? Should I go for cartridge? This is product design. And I think we're the only people who actually have a product design team at ZP. So you really need to engage in a product design team. I think we're quite a good product design team because actually we're also the manufacturers of these materials. So many product design companies are actually, their product design company have no particular specialization in biosensing, let's say, but actually when we do product design, it's with the full understanding of what product design of the final technology. I have a quick link to that. I'll try and remember to put the link underneath the video. This was something that just came up just a minute ago. So at the moment we're doing this live workshop in India. I'm involved in it, and this is just something that our head of quality just brought up. So at Zimmer Peacock, we're ISO 13485. This means that we have a documented design stage. And so when I receive questions about usability, the user needs is part of the ISO 13485 for us design procedure. So user needs have to be designed, design inputs, so needs become design inputs. We go through the design process and then we have a design output. So that is something that our product development team would actually do, is correctly sit down and actually interview the stakeholders. And the stakeholders should be people like the CEO of a company, the CSO of a company, the clinical lead of a company, some patients, but you really do, doctors, nurses, health practitioners, I should maybe classify that. The user needs have to be defined. They become design inputs. Then you go through the design process and then you have a design output. So when you're asking, I like the hypervalue electrode, but should it be in any particular format? That's really a process, actually, that has to be done formally, and it has to be documented correctly, by the way, as well. The EU and the FDA are expecting to see that done in a formal manner. Now, we're having this workshop in India, hence why I'm talking super fast, so because I'm going to get back to it in a minute. But I just want to say, these are some of the questions. Sometimes we get anodic peaks at negative voltages, a cathodic peaks at positive voltages. Why is this? Okay, so this is a simulation of a cyclophotomegram. We also do this cyclophotomegram as part of the workshop as well. And here's 0 volts. So the questioner is saying, well, I find it logical that you would have anodic peaks like that one at positive currents. That they could understand. What's confusing is, why do I have reductions also at positive voltages? So I'm going to try and explain that question really through examples. So let me transition to the next. I should say this: that voltage that we're all looking at, it's only a relative voltage. It's relative to the reference electrode, which happens in this case to be silver chloride in a chloride solution. So it's not some absolute voltage. There's this 0 volts is not absolute. It's just relative to another material that we also have in this electrochemical cell, and I'm going to come back to that point in a minute, because what it says is you take a hypervalue electrode, we actually put a solution on it, and then we're applying a voltage between the working and reference. Now that reference electrode has a standard potential of approximately 0.22 volts versus the standard hydrogen electrodes. So if there is an absolute reference in electrochemistry, it is actually the standard hydrogen electrode. Nobody uses it because it's such a pain to actually use, but it does give us a a sort of universal electrode that everyone could use. Nobody uses it. Everyone's these days using something like silver chloride. Sometimes things like copper sulfate, but mostly silver chloride. So what's happening is when you get this oxidation, what it says is that oxidation is approximately 0.55 volts versus this reference electrode, and that reduction is happening at 0.25 volts versus that reference electrode. It's just a point, and we're just now, if it was actually it could just as be that this reduction took place on the other side of the line. It doesn't matter. The potential doesn't have to. We don't necessarily get reductions at negative voltages and oxidations at positive voltages. All it says is the reduction potential for that molecule happens to be at a higher voltage than the standard potential for the silver chloride. I'll try and illustrate it a little bit with this example again, which is ferricyanide. If I put a line in for ferricyanide, what this kind of tells you is, it tells you, well, actually, the oxidation for ferricyanide essentially starts at a potential that's less than the standard potential for silver chloride, and actually the reduction, you can just about see it, is starting at a voltage that's essentially positive of that reference. So people get very, and I must admit, it took me ages to understand or get my head around this as well, that actually that 0 volts is not absolute, it's just relative to silver chloride. And so you could have a molecule that has its oxidations and reductions relative at positive voltage relative to silver chloride. You could have a molecule that has its oxidations and reductions relative to silver chloride at a negative voltage. Or with ferricyanide, it almost sits on top of silver chloride. So it's just essentially getting used to it. But it's just to say that, if you're whether you sit on this line, it doesn't super matter. You don't have to have a reduction at a negative voltage. The reduction could just as well be taking place at a positive voltage. It's only relative to the silver chloride. I appreciate it does take a little while to get your head around that because it feels quite counterintuitive. So I do recognize the pain, and I have been there myself. Somebody's asking here how to fabricate electrodes and which one is also low cost. It's probably worth saying that low cost only comes with high volume. And this will actually come to a point I have a nice question coming in from Canada. And there they want low volume, and I'm able to offer low volume at low cost. Because actually what's happening is I'm manufacturing the hypervalue carbon electrodes in high volume. So whenever you ask a question, I want low cost, what you need to get low cost is high volume. Essentially, if you're going to produce 10,000 electrodes, that's low volume, it's going to be high cost. So to get low cost, you need high volume. If you want low cost, but you only have low volume, you will get low quality. One of the biggest problems in the world of screen printed electrodes is a lot of R&D electrodes that are available are made in low volumes. And so people get low quality, and it's because you open a catalog up, there's 40 different designs. You order one of those designs. They're producing those designs in really quite low volumes. So low volume plus low cost equals low quality. And that's why I have a tendency to say to people, please get onto the hypervalue carbon electrode. We make loads of them, and we really check the quality on those. So that's me. So if you want low cost, you do need high volume. And one of the lowest cost ways of making electrodes, admittedly, is thick film printing. The question here is what it is when we do these workshops, we would do like a first scan and then get a second scan, and the first scan sometimes looks a bit different. And what happens is on the first scan, we might start off the scan here, we might start the scan here, we might start the scan here. Depending on where you start, you can end up distorting the first scan because you didn't start it at what's called the open circuit potential. So I understand what the questioner is asking, because it's like, the first scan didn't look like the second scan. Well, the first scan has an artifact in it, which is we actually started the experiment. The second scan, everything's equilibrated, and we essentially start the we start the second scan in a perfect condition because actually we've gone through the first scan, all the artifacts took place in the first scan, and then the second scan. When you're looking at beautiful data in scientific papers, it's often the second scan they're actually showing you. So the first scan could sometimes be distorted just by the process of where did you start the actual experiment. It's sometimes best to start the experiment on open circuit potential, and that is an option in at least in the software that we ship. What's the cleaning process for glassy carbon electrodes? I do actually have a link for that. There's quite a nice video here, cleaning cloths, cleaning slurries, and I have a link to it. What's the role of the electrode area for precision and range of analyte measurement? Strictly speaking, precision and area, if it's an amperometric sensor, they go together. You know, if I have a range of areas, I'll get a range of signals, and that will really affect my precision. So you've got to control on area, especially in amperometric. In potentiometric, it doesn't matter. Area is not part of the equation. This person wants to have a resolution of 0.5 millimole. There's no real big issue with that. At least 7 days of measurement. I understand it. This is I've put the link here because I want you to understand that I just found this link, this image this morning. This is a Dexcom sensor. I just want you to understand that because they were asking about, you know, the size of electrode. This is the Dexcom sensor. I suspect, I don't have first-hand evidence or knowledge, but I suspect that wire is about 100 micrometers across. So that makes this approximately 1, 2, 3, 4, 5, maybe half a millimeter. So I just want you to know, look, when you're asking about area of electrodes, probably in CGM and, you know, glucose and galactate, Dexcom, this is probably 100 microns in diameter, and it's probably about I counted 5 of them, so that makes it 2.5 millimeters long. So from that, you can work out the area of electrodes. You know, so if you're asking what kind of area of electrode is, I would just give you an example to say, have a look at this commercial example. As again, we're having this Indian workshop, we put up a slide, people, and we say, look, you know, glucose sensors, you know, we can run these glucose sensors for a very long time. And then somebody did ask, what are all those spikes? So these spikes are because sometimes we pick up the sensors and put them into a test solution. When we move the sensor, we don't necessarily stop the data acquisition, we just do it quickly. So those spikes are really an artifact because we were moving the sensor from solution to solution. Again, I am talking rather fast. I must admit, I'm not sure of the power requirements for our wireless communication. I literally don't. So I'd have to go and ask an engineer, and I'm not able to answer it at the moment. Have these sensors been tested in bodily fluids? Yes, I mean, this is really what we do. We do have a project out there called Fish Tag. If you Google Fish Tag, you will see that we're putting sensors into, you know, veterinary applications, and we do a lot of contract development, contract manufacturing for other people, and so we do see biofouling. It happens, and I don't really have a ideal solution for you on biofouling. I think it's going to happen, and you have to. When you shut down one biofouling mechanism, the body will come up with another way of dealing with it. So I don't even like to talk about it because I know, you know, how clever the body is at actually biofouling materials. And I did sort of say that I'm not super enamored with the idea of non-enzymatic glucose sensors. You can use boronic acid complexes. People are doing that. The thing about the enzyme is it's been hundreds of millions of years in development. It's got really quite good at its job, you know, let's say for glucose oxidase. And so when people are then able to design a boronic acid complex and say, you know, that's as good, I'm sort of skeptical, to be honest with you. You can also detect glucose directly. I think if you applied like 1.3 volts versus reference, you might even be able to see glucose directly, but it's very non-specific because you're oxidizing everything at that point. I don't think it's worth the effort, and I would generally, if I was making a glucose sensor, I'm super biased, you know, I'm a bioelectrochemist, I would use glucose oxidase. It works. There's no need to reinvent the wheel there. What this person is asking here is, when you do chronoamperometry, we do explain this in the workshop, you know, you see this spike, and then it relaxes, and then we start the actual experiment. This spiking is due to charging current. They ask, would you not see the same in cyclovoltammetry? Yeah, strictly speaking, you should. sometimes you don't see it because actually the main signal is so big that it actually diminishes it. And also in the software, we sometimes leave a little equilibrium time so that we start the experiment, but we don't record for the first 1 or 2 seconds, and that hides it. But you're right. If we didn't get it in the experiment, I'm sort of surprised, and it may be because we actually didn't collect that data at that point. There's actually a software setting. Somebody was asking us about how to coating strategies. So at ZP we've got lots of coating strategies. We've got robotic drop coaters, we've got dip coaters, we've got electropolymerizers. This is what we do. We're an ISO 13485 contract developer, contract manufacturer of electrochemical biosensors, and dip coating, spray coating, drop casting, electropolymerization, electrodepositions. These are the kind of technologies that we have access to. And the only difference is we do it at scale and within the confines of a quality system. How do you know the best sensor modification for our experiments? I don't think you can know. I think you have to try them, is the quick answer. There's plenty of techniques to try, and that's, at least in a research capacity, that's part of the job, I would say. Somebody was here, when people come on our workshops, we definitely have them fabricate a biosensor and definitely test a biosensor. So they were asking whether the solutions were available. They are. The solutions that we make available here are really for R&D purposes. If somebody really wants to use these solutions for, let's say, making a commercial glucose sensor, then you really have to have a quality agreement with us, because it's critical that these things perform, obviously. Somebody was asking whether a third generation sensors are commercially available. Third generation just means that enzymes are often talking directly with the electrode. They're not. There's not a third generation glucose sensor or lactate sensor on the market. Somebody was asking whether they got lower linearity with a Gen 2 glucose sensor as opposed to a Gen 1 glucose sensor. And I was just saying, if you need to get greater linearity, just increase what's called the barrier layer. If you're not sure of the barrier layer, please come on the workshop, because actually we do talk about it a lot. But I know this person was, so it'll be pretty cool. How the material coating happens on the electrode. And they asked, does it relate to repeatability? If you want repeatable biosensors, you have to have repeatable processes, and one of the main processes that's probably not repeatable in a laboratory setting is coating. So yes, you can't have a repeatable sensor unless you have repeatable processes, and coating is just probably one of the biggest sources of variability in an R&D setting. Question number 3 was somebody wants some of our sensors in smaller pack sizes. I'm really sorry that we actually don't provide these sensors in smaller pack sizes. We only provide them in the big pack sizes. I'm really sorry to say that the only sensor that we do provide, or not only, but one of the few ones we do, if it's carbon, I just ask people really strongly to actually just use the hypervalue electrode. I think question number 1 was actually a good example where somebody's used it, they've liked it, and now they want to talk about using it in a commercial setting. The reason people like it is because we are able to offer it at low volume. So I'm able to offer these electrodes at something like 50 cents at really low volume, because we're doing high volume manufacturing. So if you want low cost, high quality, you need to have high volume manufacturing, and this is the guy that we do manufacture at high volume, and therefore I can sort of stand behind its quality. It's really quite good. So unfortunately I don't do the pack sizes, or we don't do pack sizes in small ones here. If you want small pack sizes, you can definitely get them on the ZP hypervalue electrode. One of the things that concerns people, and I also wanted to make the point in question 1 as well, is our electrodes are very forward thinking. We're thinking about actual products coming from this, not just the R&D setting, but people do get very concerned about how to functionalize that. We can hand pipette 3 drops along there. We let the drops merge and then dry, and that was be one way of doing drop casting or drop coating to form the functional layer on top of that. Right, so the questions are bespoke screen printed electrodes. I think it's really interesting actually, because what's happening here is you're sort of looking at the screen printed electrode and saying, right, I'm going to put all my problems onto that screen printed electrode. For me, if you're going to do that, go with a glucose strip type design, or start thinking more broadly and actually thinking about user requirements, because those become design inputs. Then you have a design process, then you have a design output. And if you're looking for an ISO 13485 qualified product developer and product idealization, actually, that would be us. Questions from the workshop in India. Thank you for attending. Like I say, I've just made a point of answering those questions here. I also did answer them in the workshop as well, but I wanted to just put a bit more meat on the bone here. And the question from Canada. First of all, I do apologize. We don't do small pack sizes on those particular ones, but I would recommend our hyper-value carbon electrodes. They're pretty good. So that's it. I've talked fast. I have to run and get back into a workshop, but I do appreciate your attention this morning. And there's a vlog at 8 a.m. on Sundays, and then there'll be the ZP Developer Zone next Thursday at 8 a.m. London time. Otherwise, take care. Thank you very much.